So good afternoon, everyone. My name is Feng Miao. I come from Stan's group of HQ Labs. So today I'm going to talk about the characterizations of switching and thermally activated processes in low current titanium oxide memristive devices. I work closely with Joshua, Julie, myself, and Jill. So this is my outline. I start from the motivation of research in low current memristors, followed by the fabrication and device geometry of low current titanium oxide memristors. So for data discussion, there will be two parts. So in the first part, I'll just talk about some basic characterizations of low current switching in such devices. And in the second part, I will focus on the thermally activated processes, including the initial conductance, transient decay, and the switching process. Finally, I will give a brief conclusion. So, since power consumption is one of the most important parameters for memory application, as shown by the IPR's data here, so you can see that all those lower technologies are trying really hard to beat those baseline technologies. At the same time, memristive devices have big advantages in power consumption when compared to those traditional memory technologies, because they can be operated at low voltage and potentially really low current. So actually, people have already stepped into the field of the low current switching of different memristive systems, including the copper-doped silicon dioxide, hard oxide, titanium doped nickel oxide, etc. Actually, by the data here, actually the sub-1 nanoamp switching has already been demonstrated in such copper-doped silicon dioxide system. So, what about the titanium oxide memristive devices? So, in our previous work, we have already demonstrated the titanium oxide memristive devices have already shown some very good switching properties, as shown by the data here. And those switchings usually have the current level about 200 microamps. So, our work here is try to investigate a different switching mode with reduced current level and try to investigate the related physical mechanisms. So as shown by the FM picture here, so our devices usually have the crossbar structure with 50 by 50 nanometer wide electrodes, and they are fabricated by nano imprint. So usually the titanium oxide layer is about 8 or 18 nanometers, and they are sandwiched by two platinum electrodes, and they are fabricated by the sputtering. So by forming the device with reduced voltage and relative low current, which is sub 100 microamp, we find the devices actually can be switched at a different mode, as shown by the data here. So in this mode, we find the reset current actually is sub 5 microamp, which is over 10 times smaller than the typical nano devices. And for those switching modes, they usually have the low reset power, which is smaller than 0.02 milliwatt, and the set power is smaller than 0.16 milliwatt. And the on-off ratio at 0.5 is typically 2 to 3 decades. And the off-state resistance at 0.5 reaches value about 1 giga-ohm to tele-ohm with actual low reading power. So we also did some more characterizations on those devices. So to measure the switching speed, we apply the pulses with certain voltage at different pulse widths. And then we plot the 0.5 resistance as a function of the pulse width. So as shown by the data here, those are the speed for the on switch and the off switching. And we can find those devices can be switched as fast as 1 microsecond. And as shown by the here, for the on switching speed, actually find for the large device, we got a faster speed. And we also did some retention study on those devices, and we observed the initial transit at the on state. As shown by the data here, we find the 0.5 resistance at the off state is quite stable. Other devices is switched on to on state, and the devices recover to some more stable state, which is actually more resistive. And the on-off ratio at the steady state is still around 2 decades. And after measuring the device for the longer time, we find if we define the threshold resistance to be about 1/10 of the off-state resistance, and the retain time of this device usually is about 1 week. And so for this initial transit and on state, I will talk more in later in the second part of today's talk. Here, we also have some very preliminary data on the device performance and chip operating temperature. And we find there's one device which can be switched at 85 C. And shown by the data here, there's another device which survives after the temperature cycle up to 100 C. And shown by the data here, both on and off states behave as an insulator, and the off-state resistance remains identical after the temperature cycle. And the on-steady state resistance becomes about 4 times more resistive after 2 temperature cycles, which is acceptable by considering the 2 decades of operation. And as I said, here is just some very preliminary data out of a few devices, and the more work on repeatability is still needed. So now let's move to the second part of today's talk. So in this part, I'll focus on the thermal activated processes in such devices. So let's first focus on the initial transit of such devices. As shown by the data here, we monitor the conductance and fraction of the time for about half hour. And here, we recorded about 10 transit out of one device after refreshing the device to on state each time. And from data we can see, even the conductance of the transit start from the very, very similar values, and for each one, they can be fitted nicely by the single exponential decay. They are not identical. So a better descriptive way to do is as shown by this black curve. This one is the average curve out of the 10 transit. And this average curve can be fitted nicely by the stretched exponential law, which is a universal phenomenon observed widely in disordered solids. So such non-deterministic nature of the initial transit indicates the disordered nature of the active layer of the titanium oxide after the formed state. So to do some quantitative study, we studied the temperature dependence of those devices. And shown by the data here, so for each temperature, we took a set of transits. Since each transit can be fitted nicely by the exponential decay, so we can plot the log 1 over time constant versus 1 over temperature. So we find that those initial transit is actually thermally activated. So by using the linear fitting, we can extract the activation energy for those initial transits. At the same time, we also plotted the log conductance of the same device versus 1 over T on the right axis. And similarly, we can also extract the activation energy of the connection for this device. So next, we also did more devices as shown by this blue curve and the green curve here. And we find the obtained activation energy of transit agrees with the activation energy of the conductance for all those 3 devices out of 3 different batches of samples. As data summarized here, and we got the activation energy of the transit range from 50 to 210 millieV, and our results indicate that this initial transit is related to the trapping or other electronic effect. So, interestingly, if we compare the sample 1 and sample 2, which have very similar activation energy, we can find actually this activation energy is not related to either titanium oxide thickness or the switching polarity. And if we compare the device 3 with these 2, the sample 1 and sample 2, because the sample 3 has a slightly larger activation energy, and we find this value could be related to the on-off state resistance. And also, we also studied the switching process. Since the off state is usually more stable, so we studied the temperature dependence of the on switching speed. As shown by the data here, we find for higher temperature, we got a faster switching speed. So here, if we define the time constant to be the time when resistance reaches the half value of the off-state resistance. And so we can plot the log 1 over switching time constant versus 1 over T. And we can extract the switching activation energy, which is estimated to be about 1.1 eV. So this value actually is larger than both connection activation energy and the trap levels with defective do-tell. And our results indicate that although with the coexistence of the electronic effect, the switching is still dominated by the ionic motion under externally applied electric field. So this is my conclusion. Sorry. So we observed the low current switching mode in our nanoscale gallium oxide memristive devices, and we characterize them. We got the switching speed about 1 microsecond, and we find good performance at chip operating temperature for one device. And we also observed the initial transient of the on state, which is thermally activated. And this transient activation energy is small and identical to connection activation energy, indicating the trapping or other electronic effect. We also started the thermally activated switching process. And the obtained switching activation energy is about 1.1 eV, indicating the switching process is still dominated by ionic drift. Finally, I would like to acknowledge my colleagues in HDLab and the support from DARPA CNAS project. Thank you for your attention.
Okay. Any questions? Yes.
For the transient, do you apply the switching voltage and then hold it over the entire course of the transient? Or
No. It's we just apply either a pulse or a switch to switch the on.
Okay.
And we just monitor the 0 bias resistance change. So we didn't apply any bias. Yes, please.
Your retention looks like it's starting to die after a couple of weeks. So what do you do for a couple of years?
Yeah, so because right now our research on low current switching are still at the very beginning stage. So we are trying to first understand the physical mechanism of those devices, and then we are trying to improve the retention by trying different fabrication methods.
And the retention and degradation is because of the diffusion of the ionic species?
Yes, we believe so. But the initial transient is related to some trapping or other electronic effects.
I'm just a little puzzled. If I remember Stan's talk yesterday morning, in titanium oxide, the switching speed could be up to or down to about 10 nanoseconds, and you have 2 or 3 orders of magnitude slower switching speed.
Yeah, so
am I missing something, or
I think because this device actually, as I showed you the motivation, I showed the standard switching with a current level about 200 microamp. So we call those normal switching. But for those kind of switching, we have the received current as well as 5 microamp. So we believe the device actually are switched as a totally different switching mode. So in this, for those 2 different switching modes, we probably have a different switching properties. So that's the reason why we started trying to understand what's the physical mechanism of those low current mode switching.
Is the low current sample is the same with the normal one?
I would say for some of the devices, we can observe both normal switching and low current switching. But for some other devices, we can only observe the normal current level switching. So but at this point, we are still not sure what's the difference behind that.
If you give some current compliance current a little bit higher than the small current mode, then maybe it can switch to the normal switching mode.
Yeah, it's a very good point, but actually I don't think the current compliance mode is doing anything here, because when we form a device, we didn't apply any current compliance.
Maybe higher voltage.
Yes.
For set voltage.
Yes, you are right. If we apply like larger voltage, and then the device will be formed at higher current level, and then we'll go to different switching mode.
All right, thank you very much.